Video we are going to learn about the basics of trees, basic terminology what we use in the trees. So basically the tree is a nonlinear data structure and it will be in the form of hierarchy and no loops are allowed in the tree structure. So we can say that tree is a special case of the graph without any loops. So this is how basic tree structure will be looking like general tree. So we can say like here this is A is a root and now like we are having different levels. So A that is root is in level 0, next level 1, level 2, level 3 it will go on increasing as the leaf levels increase. And now right from the root to the leaf node we'll call the height of the tree actually. And here as I told you A is a root and this is edge in the case of tree and D is a parent node. And now we can say like actually A is a parent to D, D is a parent to I is a parent to Q, like this we can say. And B, C, D are siblings and now E, F are siblings. G is not having any sibling, H and I are siblings again. Now M and O, these three are siblings, P, Q are siblings, okay, like this. So E is a left child for B. Now this is called as a subtree. We can say like right from B, E, F, J, K, M also is subtree. Now like a part of a tree we can call as a subtree which comes under a one particular section is nothing but subtree what we call connected one. Then all these J, K, M, N, O, P, Q all are called leaf nodes. So let us see about the properties of the trees. There is number of edges. How many edges we will be having in a tree? Means if a tree is having n nodes, then we can say that we can have n minus 1 edges actually. And the basic property of the tree is like there is only one path from one node to another node. We'll have only one path. There will be no multiple paths actually. So depth of the node is like right from the depth of the node is defined as the length of the path from the root to that node. So right from the root to that particular node, how means like that length is nothing but what we call as a depth of the node. So how many edges are there right from the root to that particular node, we call it as a depth of the node. For example, if you consider this one, now if I want to find the depth of F, 1, 2, two edges are there, right? So 2 will be the depth of F actually. Height of a node. So height of a node is nothing but right from the node to the leaf node. Longest path we will be calling as a height of that particular node. For example, if you consider the height of B actually. So from B to M actually, that is leaf node. So from B, one edge and second edge, 2, right? So height of B is 2. Suppose if I want to find height of A, then 3. Suppose height of F, 1. Like this we can calculate the height of a particular node. Then height of the tree means right from the root to the leaf node. That is height of the tree. Then degree of a node. Degree of a node is total count of subtrees attached to that node is called the degree of the node. Normally in the case of graphs what we have done, how many edges are connected to it, that we have counted as a degree. But here we can say like how many child nodes we are having for a particular node, that is nothing but degree of a node actually. So there are different types of trees: binary tree, ternary tree, and array tree. So in the case of binary tree, each node will be having at the max 2 child nodes. Ternary tree means each node will be having at the max 3 child nodes. So it means that it can have either 0, 1, 2, 3 child nodes actually in the case of ternary tree. And array tree means n child nodes can be existing for any node in the tree. So if you consider like some special types of trees, just definitions we are going through here. In detail, we'll discuss these trees later. So in other videos. Binary search tree. So what is binary search tree means? The parent will be in between the child nodes. So the value will be in such a fashion that the parent will be between the two child nodes. Suppose if you see like 18, 25, 34. So 25 is lying between 18 and 34. If you see the binary search tree, the values which are less than the root will be coming towards left of the root. Values which are greater than the root will be coming towards right of the root. So we can say that like a node whose value is less than the parent will be inserted towards left. If it is greater than the root or parent, towards right we will insert actually. That is binary search tree. AVL tree. AVL tree is a self-balancing binary search tree where a difference between the heights of left and right subtrees of for any node cannot be more than 1. So at any part of the tree, if you consider in the AVL tree, the height of left subtree minus right subtree can be 1. Okay, so here if you see like right from complete tree, if you are considering, we are having the height of left subtree. The maximum height is 1, 2, 3. So 3 is the height of left subtree. Right subtree is 1, 2. Right? So 3 minus 2 is 1. Now if you consider from 18 actually. So this side 18, 2 we are having and this side 1 we are having. So that is nothing but we will say that the difference between the left and right subtrees can be at the max 1. That is nothing but AVL tree. The next one is the red black trees. The red black tree also is another kind of self-balancing binary search tree. And here the nodes will be colored with red or black. Okay. The root of the tree is always black. No, we are defining this. Root should be always black in color, and no two adjacent nodes can be red in color actually. So we can have two adjacent nodes to be black in color, but we cannot have two adjacent nodes to be red in color actually. So every path from a node to any of its descendants null nodes has the same number of black nodes. Means whatever the path right from the root to the leaf node, after the leaf node will have null nodes in the case of black trees. So we'll have like right from the root to the null nodes, the number of black nodes will be same. Any path you take from the root to the null nodes actually. So all null nodes again are black in color. So this is an example for red black tree. Now if you observe here, we are having the root as black in color, and you can observe another property, that is no two adjacent nodes are red in color, and we can see like the all null nodes, the square way represented nodes are nothing but null nodes here. So all null nodes are black in color. Now if you, another property of red black tree is the number of black nodes is same in any path. Now if you say like 7, 3 and null node, like we are having 3 null black nodes, similarly this one also, and now 7, 10 and null node 3, 7, 10 and another, all the child nodes which are coming under subtree of 10 are included in this. Now 7, 22 and null nodes, right? So if you consider any path in this particular red black tree, you are having 3 black nodes. Okay. Next, B tree. So here B tree, what happens here is like will be the structure of the node is different when compared to the other trees actually. Like we are going to have more number of keys in a single node. So how we are going to have the minimum number of keys, maximum number of keys, etc. and all we will see in video in detail of B tree actually. So here you can see like again like this is also similar to your binary search tree, but only the difference is we'll have more number of keys in each node actually. Okay, so what will happen here, the values which are less than 150 will be coming towards left, values which are less than 50 will be coming towards left of 50, values lying between 50 and 75 will be between 50 and 75, and values greater than 75 will be right of 75. Now values greater than 150 will be coming towards right of 150. Similarly, values less than 160 will be left of 160. Between 160 and 185 will be having in between these two numbers, and values which are greater than 185 will be right of 185. So this is how your B tree will be. Next, B plus tree. So the difference between the B plus tree and B tree is we'll be having all the values in the leaf level itself for the B plus tree. Some of the values will be repeated. So multi-level indexing concept is incorporated in the case of B plus tree here. So if you observe, like 7 is repeated, 17 is repeated, 25 is repeated here. And there is a link between all the leaf nodes, and if you see like the leaf nodes in the B plus tree, they will be in the increasing order. So 1, 4, 7, 10, 17, 19, 21, 25, 27, 35. Like this, they will be in the increasing order, and all the values will be having at the leaf level. Some of the values will be repeated as internal nodes and root nodes, which we call them as index actually instead of values. Then another type of tree is segment tree. So now let us consider this example. Array we are having 1, 3, 5, 7, 9, 11. So how we are going to have the segment tree is the sum of these values 1 plus 3 plus 5 plus 7 plus 9 plus 11 is 36, which will become as a root. So 0 to 5. Array will start with index 0, so 0, 1, 2, 3, 5. That is 0 to 5 values we are having, whose sum is 36. We are making it as a root. Now we'll split this into two parts. So 0 to 2 and 3 to 5. Okay, so 1, 3, 5 will be coming to this, and 7, 9, 11 will be coming towards right. So 1 plus 3 plus 5 is 9. 7 plus 9 plus 11 is 27. So we'll get towards right of 36. Now you can see that this is not like binary search tree, okay, because 27 is not greater than 36. Now coming back to this, like 9, 0 to 2 elements we are having. So what do we do? 0, 1 elements we are taking towards left, and second element we are taking towards right. So first two elements, 1 plus 3 is 4, and in the case of 3 to 5 elements, 3, 4 elements we are taking towards left, that is 7 plus 9 is 16, and fifth element, that is 11, we are taking towards right. Now 0, 1, we are taking 0 element towards left, first element towards right. In the case of 3, 4th element, so third element as left and fourth element as right. So what happened here, till we split them into single element, the tree structure will be formed. So like this, the array is represented as segment tree. So these are the different types or special types of trees. Thank you.